In this video, we're going to look at derivatives with respect to other variables, and the first example we're going to look at is the derivative of x cubed with respect to x. So in this one, we have a match between the variable that we're taking the derivative with respect to, x, and the variable in our function, x cubed. So when we find the derivative of this, we're going to get 3x squared. Now, something that we haven't been writing in, but is actually still there, is that we're also multiplying by the derivative of x with respect to x. The reason that we're not writing that in is because it is equal to 1. The derivative of x with respect to x is telling us how x changes when x changes, and that's a one-to-one relationship, so it's just equal to 1. That's why our derivative would just be 3x squared. Now if we look at another example where instead of having x cubed, we have 2x plus 5 cubed, again taking the derivative with respect to x, this is a situation where we would have to use the chain rule because we have one function of x inside of another function, the cubic function. So the 3 would come down, the 2x plus 5 would stay the same, we would subtract 1 from the exponent, and then we would multiply by the derivative of the inside. So we would be multiplying by dx of 2x plus 5. So that's just the chain rule, saying that we take the derivative of the outside, multiply by the derivative of the inside. So the derivative of 2x plus 5 is 2, so we'll have 3 times 2x plus 5 squared times 2, which will give us 6 times 2x plus 5 squared, and that would be our derivative. So now let's take a look at an example where our function is not in terms of x, but now in terms of a different variable. So let's look at taking the derivative with respect to x of u cubed. So importantly here, we have a mismatch between our variables. We are taking the derivative with respect to x, but our function that we're taking the derivative of is with respect to u. Now, that said, what we are going to do is we are going to treat u as a function of x. So, in other words, this is going to be very similar to what we just did. So the 2x plus 5 in the previous example is almost like the u in this one. So we have some function of x, we just don't know how it's defined, being cubed. So when we take the derivative, the 3 is still going to come down. The exponent will be subtracted by 1, so we'll have u squared. And then we're going to take the derivative of that inner function. But in this case, it's u. We don't know how it's defined in terms of x, but we're treating it as a function of x. So what we end up with is 3u squared times the derivative of u with respect to x. We don't know what that is, so we leave it as du dx. So in the previous example, we were able to find the derivative. We worked it out to 2, but in this one, we don't know how u is defined in terms of x, so we just leave the placeholder of du dx, which is the rate of change of u with respect to x. So that's an example of taking the derivative of a function with respect to a different variable. So we had that mismatch in the variables. We still treated the variable in the function as if it is a function of the variable that we're differentiating with respect to, which in this case was the x. So let's take a look at some more examples. So let's say we want to find dy dx for y equals 5u squared. So again, we're taking the derivative with respect to x, and our function is a function of u, but we are going to treat u as if it is a function of x. So when we take the derivative of this, and I'm going to write this in this way. So d by dx of y is equal to d by dx of 5u squared. Because when we take the derivative and we end up with that dy dx, really all we're doing is we're doing d by dx of y, and that's where the dy dx comes from. And then with the d by dx of 5u squared, we'll have 5. Then using the idea of the chain rule, the derivative of u squared is 2u. And then we multiply by the derivative of u with respect to x, the derivative of the inside, but again, we don't know how it's defined in terms of x. We're just treating it as if it is a function of x. So that would give us then 10u times du dx. So that would be the derivative dy dx for y equals 5u squared. And again, we end up with the du dx because we were taking the derivative with respect to x, and our function contained a u, and we treated that as a function of x. So let's look now at finding dy dx for y equals 3r minus 2r squared. So again, we have a mismatch in our variables. We are differentiating with respect to x, and our function is a function of r. So we're still going to do the same thing. We're going to treat r as if it is a function of x. So when we take the derivative, so taking the derivative of both sides with respect to x, the variable here, when we take the derivative of these r terms, we're going to end up with a dr by dx. So we have dy by dx is equal to the derivative of 3r, so that's going to be 3. The derivative of r on its own is 1. But then we are multiplying by the derivative of r with respect to x, minus 2 times the derivative of r squared. Again, r is being treated as a function of x, so this is going to be 2 times r, and then multiply by the derivative of the inside, the derivative of r with respect to x. So what we end up with is 3 dr by dx minus 4r times dr dx. And because both of these are multiples of dr dx, we could factor the dr dx out. I'm going to put it at the end and say that this is 3 minus 4r times dr by dx. So that would be the value of dy by dx. So it would be 3 minus 4r times the derivative of r with respect to x. So now let's say we want to find dp by dt for p equals 6y cubed minus 2y. So we're taking the derivative with respect to t, and now we have two different variables in our function. We have x and y. So in this case, we're going to treat x and y as variables of, or sorry, as functions of, because we're differentiating with respect to t, of t. So we're going to treat x and y as functions of t. And because they're both functions of t, that means when we have this multiplication, the x times the y cubed, or the 6x times the y cubed, we need to use the product rule because we have two functions of our differentiating variable, t, that are multiplying together. For the minus 2y, we don't need to worry about that. It's not multiplying a function of two functions. It's just the one function of t. So we'll need to use the product rule. So dp by dt is going to equal, and I'll write off to the side, I'll use u and v to represent our two functions. So u will be 6x. So then du by not dx but dt, because we are differentiating again with respect to t, is equal to 6. Then the derivative of x with respect to t is not 1, but it's 1 times dx by dt. And again, we're doing that because we're differentiating with respect to t, and we're taking the derivative of this x, so we're treating that x as if it is a function of t. Then v, our second function, will be the y cubed. So then dv by dt will equal 3y squared times the derivative of the inner function, so times the derivative of y with respect to, again, t, because we are finding the derivative with respect to t. So now that we have our two functions and their derivatives, we can go to the product rule. So the product rule says that the derivative is going to be the derivative of the first, so 6 times dx by dt, times the second, so times y cubed, plus the first, 6x, times the derivative of the second, which in this case was 3y squared, times dy by dt, minus, so that's the product rule part, then minus 2 times the derivative of y with respect to t. So cleaning this up a bit, we get 6y cubed times dx dt plus 18xy squared times dy dt minus 2 times dy dt. And then we could factor the dy dt from these two terms to say that this is 6y cubed times dx dt plus, then I'm going to put brackets, 18xy squared minus 2 times dy by dt. And that would be our final answer for dp by dt.